Hello everyone. So now let us look at the relative stability analysis using RH criteria. So this relative stability analysis is basically on the basis of dominant roots. Okay, so dominant roots are those roots which are lying closer to imaginary axis, and the dominant roots are basically affects the transient response by making the system more and more sluggish. That's because lesser the value of zeta omega n, greater will be the settling time. Okay, so relative stability analysis basically helps us in finding out the presence of dominant roots closer to the imaginary axis. Okay, so how are we going to do it? So let's say, for example, we have a characteristic equation of a system. Let's say some random system I will consider. Let's say some sq plus 10s phi plus is equal to 0. So it's a sixth order system. That means to say there are 6 roots. There are 6 roots. Now, the one of the drawback of Routh-Hurwitz criteria is that it just tells about the presence of closed loop poles on RHS of the S-plane, or how many there in the LHS of the S-plane. So only you will come to know about the root count. You will not be able to know about the exact locations or where exactly those 6 roots are placed. That information you cannot get it from the RH criteria, right? So that's the reason it is pretty difficult to understand how many dominant roots are present in this particular characteristic equation. A way to understand the dominant root nature of a given characteristic equation is from the relative stability analysis. Now, in relative stability analysis, what we do is that we think of shifting the axis. Okay, normally, you take the axis, j omega axis, starting from the origin, right? But in case of relative stability analysis, what we do is shift the axis. This is what we do. Shift the axis. Now, where to shift the axis? You have to shift the axis where your interest lies. In the sense, let's say you want to find out how many roots which are lying right off of, let's say, -2. So if that is the case, you have to put the default s value with s is equal to s minus 2. Okay, so by doing so, what happens is that you are going to change the axis of interest from origin to a newer location -2. So this is your -2. Why -2? I've just taken a random number. That's because -2 is very close to origin, right? So I can say that, okay, within this region, if I find any roots, I can treat them as my dominant roots, and then I can redo my engineering so that, I will try to limit the presence of dominant roots in this particular pole zero plot, because dominant roots are going to affect the transient response by increasing the settling time. Now, what we have done is we have shifted the axis to a newer location, which is at -2. So that's the reason what you have to do is you have to put s is equal to s minus 2 in equation 1, where your equation 1 is nothing but the characteristic equation. Now, by doing so, what you are going to do is you are going to modify your characteristic equation to a newer location, which is our point of interest. point of interest. So the modified characteristic equation, let's say f dash of s is equal to, in place of s, what is that you are going to substitute? S minus 2 cube, to the power 6 plus 10 into s minus 2 to the power 5, 4 into s minus 2 to the power 4 plus 8 into s minus 2 whole cube plus 4 into s minus 2 square plus 12 into s minus 2 plus 18 is equal to 0. So you solve this particular equation and then you try to get the polynomial of s, something like s cube plus s5 plus s4, so on and so forth, along with some coefficients, say a, b, c, blah blah blah. Okay, that you can do it all. Okay, now once you get this new expression f dash of s, what you can do is you can reapply the RH criteria. Okay. So algorithm, you have f of s, you have to convert f of s into f dash of s by substituting s is equal to s minus alpha, where alpha is it's an integer, okay, where alpha is say point of interest. In our case, we assumed alpha as 2, alright, f dash of s. Now, once you get f dash of s, you examine the stability. How do you examine the stability? By applying RH criteria. Now, while examining the stability, if at all you observe, okay, by examining the stability, okay, you can say that, you can just put a decision block, something like sign change. Okay, so this is our decision block, sign change. If yes, then you can say that there are roots falling in RHS of s minus alpha. Right. If there is sign change, then there are roots falling in RHS of s plane, and number of roots is equal to number of sign change. On the other hand, if in the RH criteria, in the RH root array, if you don't observe any sign change in the first column, okay, obviously the sign change becomes n. If there is no sign change, then you can say that no roots falling in RHS of s minus alpha. That means to say no roots are lying on RHS of s minus alpha. So you can say that no dominant roots. So this is nothing but no dominant roots. On the other hand, if your condition is yes, then there are dominant roots. There are dominant roots. How many dominant roots? That you will come to know by checking the sign change. Okay. So this RH criteria can be used as a powerful tool to determine the presence of dominant roots at the desired point of interest. So this alpha value in problems, normally they will mention alpha is equal to -1, -0.5, -2, etc., etc. So whatever may be the value of alpha, what you have to do is that You have to replace S with S minus alpha, recreate your characteristic equation, say f dash of S, and then apply RH criteria, and then examine the stability. If there are sign changes, then there are dominant roots. If there is no sign change, then you can say that there are no dominant roots and your system is pretty good. Okay, it will not suffer from lesser settling time. Sorry, it will not suffer from the larger settling time. All right. So that's about your relative stability analysis. Thank you. In the previous slide, we had written an algorithm to determine the dominant roots, right? Now, once you get the information about dominant roots, in the sense the diamond block, the decision block, will give you the information about sign change, right? Okay. So if there is sign change, okay, then you will be able to know how many. You will be able to know how many sign changes are taking place. Okay. If there is no sign change, then you can simply say that no dominant roots are false. This is what is the understanding, right? Now, let's say you did not get any sign change in the first column. Okay. So, if you don't get any sign change, then you can say that no dominant roots are lying on right half of S minus alpha. So this is my S minus alpha axis, and this is my original the J omega axis, which starts from 0, right? So let's say this is KSB, and this is what you get for KSB. So all your roots will be lying on left half of S minus alpha. That is possible only when you don't get any sign changes. On the other hand, if there are any sign changes, and if you come to know how many sign changes are taking place, then those many sign changes will be taking place in a region which is right half of S minus alpha. Okay. So this is your dominant pole region. Okay. That eventually affects your settling time. Okay. So this way, we can pictorially show the presence of dominant roots. Okay, and probably you can use this diagram to explain the concept of judging the relative stability of a system using RH criteria.